When troubleshooting fuse blowing issues, firstly check the fuse amperage. Ensure that the fuse amperage matches or slightly exceeds the maximum current draw of the heater, which is given as 5 amps to 8 amps. Using fuses with too low of a rating will cause them to blow prematurely. Secondly, use slow blow fuses. Fast-acting fuses break the circuit quickly upon sensing a surge or overload. Slow-blow fuses, on the other hand, allow for brief current surges before breaking the circuit. For heaters, which often experience initial current surges, slow-blow fuses are the preferred choice. Thirdly, verify proper wiring. Check all wiring connections for any loose or incorrect connections. Loose connections can cause resistance and overheating, which can lead to fuse blowing. Fourthly, consider a primary side fuse. While not typically required, adding a fuse on the primary side of the transformer can provide additional protection against catastrophic faults. Use a fuse rated for the transformer's primary current rating, which is typically 30 amps for a 208 volts, 30 amp system. Fifthly, check the transformer rating. Verify that the transformer is rated for the power requirements of the heaters. Overloading the transformer can cause overheating and fuse blowing. Sixthly, inspect the heaters themselves. Check the heaters for any visible damage, such as broken elements or frayed wires. Damaged heaters can cause overcurrent conditions which can lead to fuse blowing. Based on the provided information, the most likely cause of the fuse blowing is the use of fast-acting fuses. It is recommended to replace them with slow-blow fuses to accommodate the initial surge current of the heaters. Additionally, consider adding a fuse on the primary side of the transformer for added protection. Let's delve deeper into each of these points. Concerning fuse amperage, understanding the current draw of your heaters is paramount. If a heater consistently draws 7 amps, a 5 amp or 8 amp fuse might still blow intermittently, especially if the heater experiences even brief spikes above that rating. It's often wise to choose a fuse rating that comfortably exceeds the typical current draw, but not excessively so, as this could compromise the safety the fuse is intended to provide. Typically, exceeding 25% of the maximum current draw of the heater will cause the heater to have too much current and cause other problems. Regarding slow blow versus fast-acting fuses, the inherent nature of a heater's operation involves an inrush current. When initially energized, the heating element requires a significantly higher current to reach its operating temperature. A fast-acting fuse, designed for immediate response to overcurrents, interprets this inrush as a fault and promptly interrupts the circuit. A slow-blow fuse, conversely, tolerates these brief surges, allowing the heater to reach its normal operating state without nuisance tripping. When inspecting wiring, pay meticulous attention to every connection point. Use a multimeter to check for voltage drops across connections, which can indicate increased resistance due to looseness or corrosion. Ensure that wire gauges are appropriate for the current they are carrying, consulting relevant electrical codes for guidance. Additionally, look for signs of insulation damage, which can lead to short circuits and subsequent fuse failures. Consider that a primary side fuse adds an extra layer of protection for the entire system. It protects the transformer itself from internal faults or overloads on the secondary side. Selecting the correct fuse rating for the primary side is crucial. It should be sized based on the transformer's volt-ampere rating and the primary voltage. The formula to calculate the primary current is volt-amperes divided by volts. For example, if the transformer is rated at 3000 volt-amperes and the primary voltage is 208 volts, the primary current would be approximately 14.4 amps. A fuse slightly above this value, such as a 15 amp or 20 amp fuse, would be appropriate. When assessing the transformer rating, it's essential to determine the total power demand of all the heaters connected to the secondary side. Add up the wattage of each heater to obtain the total wattage. Then, divide the total wattage by the secondary voltage, 115 volts, to calculate the total current draw on the secondary side. The transformer's volt-ampere rating should be significantly higher than the total volt-amperes required by the heaters to avoid overloading. If the transformer is consistently running near its maximum capacity, it can overheat, shortening its lifespan and potentially causing fuse failures. While inspecting heaters, look for any signs of physical damage to the heating elements, such as cracks, bulges, or burn marks. Use an ohmmeter to measure the resistance of each heating element. A significantly higher or lower resistance reading than the manufacturer's specifications indicates a faulty element. Also, check for continuity between the heating element and the heater's metal casing, which would indicate a short circuit. In summary, to effectively troubleshoot blown heater fuses, a systematic approach is required. Firstly, confirm the fuse amperage rating is appropriate for the heater's current draw. Secondly, switch to slow blow fuses to accommodate inrush currents. Thirdly, meticulously inspect wiring connections for any signs of looseness or damage. Fourthly, consider adding a primary side fuse for enhanced protection. Fifthly, verify the transformer's rating is adequate for the total load. And sixthly, thoroughly inspect the heaters themselves for any physical damage or electrical faults. Implementing these steps should significantly reduce the incidence of blown fuses and improve the reliability of your heating systems. Remember that electrical work should always be performed by qualified personnel who are familiar with relevant safety codes and practices. Always to energize circuits before performing any inspection or maintenance. Additionally, consider the ambient temperature in which the heaters are operating. High ambient temperatures can affect the current carrying capacity of wires and fuses, potentially leading to premature fuse failure. If the heaters are located in a high-temperature environment, it may be necessary to upsize the wire gauge and fuse rating to compensate. Furthermore, be aware of the heater's duty cycle. Heaters that cycle on and off frequently may experience more inrush current events, increasing the likelihood of fuse blowing. In such cases, using a more robust slow-blow fuse or implementing a soft start circuit can help mitigate this issue. Also, check the voltage at the heater terminals. Low voltage can cause the heater to draw more current to compensate, potentially exceeding the fuse rating. Use a voltmeter to measure the voltage under load and ensure that it is within the heater's specified operating range. If the voltage is consistently low, investigate the cause, such as undersized wiring or a voltage drop in the circuit. It's also important to consider the type of load the heater is present. Some heaters may have a purely resistive load, while others may have an inductive load. Inductive loads can generate voltage spikes when switched off, which can stress fuses and lead to premature failure. In such cases, using a fuse specifically designed for inductive loads may be beneficial. Remember to document all troubleshooting steps and findings. This will help you track down the cause of the fuse blowing issue and prevent it from occurring in the future. Keep a record of fuse sizes, wiring configurations, transformer ratings, and heater specifications. This information will be invaluable for future troubleshooting efforts. Consider implementing a preventative maintenance program for your heating systems. Regularly inspect wiring connections, check fuse ratings, and test heater performance. This will help you identify potential problems before they lead to fuse blowing or other more serious issues. Also, train personnel on proper operating procedures for the heating systems. This will help prevent misuse or abuse that could lead to overcurrent conditions and fuse failures. For example, ensure that personnel are aware of the proper way to adjust heater settings and avoid overloading the system. When replacing fuses, always use fuses of the correct type and rating. Using the wrong fuse can be dangerous and could lead to equipment damage or even fire. Never attempt to bypass a fuse or use a fuse with a higher rating than specified. This could overload the circuit and create a safety hazard. Also, be aware of the different types of fuses available. Some fuses are designed for specific applications, such as motor circuits or electronic circuits. Using the wrong type of fuse can result in nuisance tripping or inadequate protection. Consult with a qualified electrician to determine the appropriate type of fuse for your application. When working with electrical systems, always follow safe work practices. Wear appropriate personal protective equipment such as safety glasses and gloves. De-energize circuits before performing any work. Use insulated tools to prevent electrical shock. I never work alone. Have someone nearby who can assist you in case of an emergency. In addition to the above, consider using a fuse puller to remove and install fuses. This tool helps prevent electrical shock and makes it easier to grip the fuse. Also, be sure to properly dispose of blown fuses. Do not throw them in the trash. Instead, recycle them at a designated recycling center. Finally, remember that electrical codes and regulations vary depending on your location. Consult with a qualified electrician to ensure that your heating systems comply with all applicable codes and regulations. This will help ensure the safety of your system and prevent potential problems down the road. In addition to the steps outlined above, there are a few other factors to consider when troubleshooting blown heater fuses. Firstly, check for any signs of corrosion or contamination on the fuse holder. Corrosion can increase resistance and cause the fuse to overheat and blow prematurely. Clean the fuse holder with a wire brush or contact cleaner to remove any corrosion. Secondly, inspect the wiring insulation for any signs of damage. Damaged insulation can lead to short circuits and ground faults, which can cause fuses to blow. Repair or replace any damaged wiring. Thirdly, check the heater's power cord for any signs of damage. A damaged power cord can also lead to short circuits and ground faults. Replace any damaged power cords. Fourthly, if the heater is connected to a GFCI outlet, test the GFCI to make sure it is working properly. A faulty GFCI can trip unnecessarily, causing the heater to shut off. Fifthly, if the heater is connected to a surge protector, make sure the surge protector is working properly. Faulty surge protector can allow voltage surges to pass through to the heater, which can damage the heater and cause the fuse to blow. Sixthly, if the heater is used in a damp or wet environment, make sure it is properly grounded. Improper grounding can lead to electrical shock and can also cause fuses to blow. Seventhly, if the heater is used in a dusty environment, clean the heater regularly to remove any dust or debris. Dust and debris can accumulate on the heating elements and cause them to overheat, which can cause the fuse to blow. Eighthly, if the heater is used in a high-altitude environment, the heater may need to be deaerated. High altitude can affect the heater's performance and cause it to overheat, which can cause the fuse to blow. Ninthly, if the heater is used with a dimmer switch, make sure the dimmer switch is compatible with the heater. Not all dimmer switches are compatible with all heaters. Using an incompatible dimmer switch can damage the heater and cause the fuse to blow. Tenthly, if you are still having trouble with blown heater fuses, consult with a qualified electrician. An electrician can help you diagnose the problem and recommend a solution. Also remember that the National Electrical Code, or NEC, provides guidelines for electrical installations, including heating systems. Refer to the NEC for specific requirements related to fuse sizing, wiring methods, and grounding. NEC Table 310.15b16 provides ampacity ratings for conductors based on their size and insulation type. Use this table to ensure that the wiring used in your heating system is adequately sized for the current it will carry. NEC Section 430 covers motor circuits, which may be relevant if your heaters use motors to circulate air or provide other functions. This section includes requirements for overcurrent protection, conductor sizing, and motor disconnecting means. Finally, always follow manufacturer's instructions for installation, operation, and maintenance of your heating systems. This will help ensure safe and reliable operation and prevent potential problems.